Today on Impossible Engineering, the FAST Telescope, the largest radio telescope on the planet.
That is an incredible piece of engineering.
A record-breaking telescope of astronomical proportions.
Those sensors can be located to within 1 centimeter in this 500-meter dish.
And the innovative pioneers of the past.
Believe it or not, these are sound mirrors.
Who made the impossible possible. Guizhou Province, southwest China. Since the dawn of time, humanity has sought to unravel the mysteries of the universe. And physicist Andrew Steele is here, seemingly in the middle of nowhere, to see how we just might reveal the clues of the cosmos.
Tucked into a natural basin sits one of the world's newest and most advanced space exploration devices.
That is an incredible piece of engineering.
The 500-meter Aperture Spherical Radio Telescope, or FAST for short, is the largest and most sensitive single-dish radio telescope in the world.
It can pick up radio waves from billions of light years away and will help to unlock the secrets of our universe.
The $180 million FAST telescope is probing the cosmos more deeply than any radio telescope before it. Completed in 2016, it detects the radio waves emitted by objects in deep space, allowing astronomers to see what's out there on a truly epic scale. This massive 1,600-foot diameter antenna consists of a spider's web of 10,000 steel cables, weighing nearly 1,800 tons. These support a sprawling 4,450 triangular panels, which form the dish itself. And at the center, suspended from 6 330-foot-high towers, hangs a 33-ton receiver cabin. This incredible device collects data from billions of light years away. But for astronomer and one of FAST's creators, Peng Bo, building a project on such an astronomical scale is no easy task.
This is the most amazing telescope in the world. When we proposed such a big telescope, nobody believed this big dish can be built.
The first problem engineers had when constructing this thing is its sheer size. FAST is vast. And to put that into some kind of context, the previous world's largest radio telescope was 300 meters across. This thing is 500 meters. That's over twice the area for collecting those faint radio waves coming down from the sky.
So how can FAST's engineers build a receiving dish of such epic proportions? This would be impossible without history's greatest innovators. Since humanity emerged from the caves and began building homes, most designs have had one thing in common.
Fantastic. Oh, I say, it's simply marvelous.
4 walls and a roof.
Hey! Oh, crikey.
But during America's post-war housing shortage, architect Richard Buckminster Fuller bucked the traditional house, creating something revolutionary. Tasked in the 1940s with creating a quick and cost-effective method for building homes, he developed the geodesic dome house. In Cornwall, England, science communicator Kate Mulcahy is getting a bird's eye view of the geodesic concept.
Behind me is an icon in conservation and a feat of modern engineering. These are the biomes, which are part of the Eden Project. They're actually covered in a really intricate pattern of hexagons and pentagons with sharp angles and corners. This geometric feat is not just about looking good. It actually has a really important purpose.
Its designers needed to house a variety of plants from different climates, including the tropics.
Measuring 55 meters high, 100 meters wide, and 200 meters long, surrounding an area the size of 34 football pitches, the rainforest biome is actually large enough to house the Tower of London.
So how can a geodesic dome cover such a vast amount of space?
A geodesic dome is a spherical structure which is made of triangular elements that form a network of circles to create the surface of the sphere. But the real strength of Fuller's design was that it was made with a series of triangles. Now, the triangle, with its fixed angles, is actually the strongest two-dimensional shape. Now, I want to show you exactly how this works by building one of these using only these. As I'm joining the triangles together, they begin to form the shell of my structure, and the rigidity of each triangle begins to form a tremendous strength. It's only when this final piece gets added that the strength comes together. Now I have a self-supporting structure, and whatever stress I put on it gets distributed evenly across the whole structure.
Fuller's genius becomes clear when scaling up. The bigger the dome gets, the stronger it becomes. The only human-made structure to do such a thing.
But how strong is it? It's certainly very light, easy to pick up. The only way to actually test this is for me to climb on top. So, yeah, it's very strong. So we see, Fuller's design definitely works, just like the biomes behind me. Oh, amazing.
Even more incredibly, when a sphere's diameter is doubled, its surface area quadruples, creating 8 times the volume with very little surface area. This results in less materials and less expensive homes.
Wow. It's an amazing piece of engineering if you want to build something that's very big, that's very light, and that's very strong.
To create the world's largest uninterrupted dish, FAST's engineers are supersizing Fuller's geodesic dome concept and flipping it on its head.
Nobody believes it can be done. Every time I saw each component built up, I feel very, very excited.
To take on this gargantuan challenge, workers construct a 1-mile-long steel girder ring, forming the outer perimeter of the dish. 6 300-foot-high towers surround it and support a 33-ton feed cabin. This houses the all-important receiver, designed to capture even the faintest of galactic radio waves.
So in order to build such a giant spherical reflector, a geodesic triangular design is the best choice. The dish has been divided into about 4,450 panels.
After just 5 years of construction, on July 3, 2016, the engineers lowered the last aluminum triangular panel into place.
This is just an absolutely awesome structure. It's epic in scale. And those aluminium panels are perforated to keep them, firstly, lightweight, secondly, to allow the rain through, and finally, to allow the light through. That means the plants can grow on the surface underneath and their roots can get down into the soil and provide a bit of support for this truly enormous structure.
But to create the most precise telescope ever built, FAST engineers must draw on the pioneers from the past.
Suddenly, the biggest threat came from the sky. Defending against enemy aircraft was virtually impossible.
To make the impossible possible. The FAST telescope. Hidden in the mountains of southwest China, it's the largest radio telescope on the planet.
FAST is massive, and that's ideal for collecting those weak radio signals from billions of light years across the universe. But it also presents engineers with a big problem. FAST is so huge, it has to be fixed to the ground.
Smaller radio telescopes have a receiver fixed at the center of the dish to collect reflected radio waves. The dish rotates to point at the exact area under observation. But the FAST dish is too enormous to do that.
As you can see from this rather nifty little scale model, you can't just tilt the whole landscape to point FAST at a particular galaxy you might be interested in studying.
So how do you make a telescope the size of FAST point at different places in the sky? To resolve this conundrum, the team must draw on history's greatest innovations. Since classical times, a shape known as a paraboloid has been treasured for its reflecting qualities. In 3rd century BC, legend has it that Greek mathematician Archimedes used parabolic mirrors to concentrate the sun's rays and set fire to invading Roman ships.
We'll call it a ray gun. Okay, boss.
17th century astronomers searched the sky with new clarity by adding parabolic mirrors to their optical telescopes.
Boring.
And early lighthouses used them to beam their warnings out to sea.
Oi, turn the light on.
High above the Kent coast in southern England, physicist Susie Sheehy is investigating an historic moment when engineers began using parabolic mirrors on a giant scale.
World War I was the first major conflict involving aircraft, and even though it was a new technology, it had a major impact. Suddenly, the biggest threat to security came from the sky. Defending against enemy aircraft was virtually impossible, as it relied purely on sight.
That's because both night skies and cloudy days obscured incoming enemy aircraft.
And the solution to that problem is these incredible structures.
These monolithic structures once peppered the shoreline of Great Britain.
Believe it or not, these are sound mirrors.
Pioneering acoustic physicist William Sansome Tucker designed these sound mirrors, not to see, but to hear approaching enemy aircraft.
Here at Denge are some of the finest examples of Tucker's work, and they're each a slightly different size and have different structures. So the smallest one points straight out, and it collects sound waves that are slightly lower and slightly nearer. The middle-sized one is pointed further up towards the sky. And then finally, over there, is a 200-foot wall. They're all based on a curved surface known as a paraboloid. And when the sound waves come in and bounce off the paraboloid, they're all focused down to one point at the center called the focal point.
Sound waves hit a parabolic reflector at different places. When those reflected rays meet at the focal point, the sound amplifies.
I'm going to attempt to recreate an early warning scenario. So I'm going to place this microphone at the focal point. So about there, all of this area is going to collect sound waves and focus them down to the center and amplify the sound. So I've got this set up here with a laptop connected to the microphone at the center of the parabolic reflector, which is about 100 feet away. And all the sound waves are going to bounce off that reflector and be collected by that microphone. And that's represented by the blue curve here. And the red trace is a control microphone that's placed off to one side. So I'm just going to have a quick listen. At the moment, nothing much is happening. The curves are the same. I can't really see any difference.
But as aircraft approach from many miles away and from different points in the sky, the parabolic sound mirrors let sound technicians hear the engines in time to alert air defenses.
So I can start to hear something. You can definitely hear a plane propeller. So I can definitely see that the blue curve is above the red one in this middle region here. And historically, we could use these sound mirrors to detect airplanes about 15 or 20 miles away.
To detect radio waves from different areas in the sky without moving the telescope, FAST's engineers are revolutionizing the concept of multiple parabolic sound mirrors with a single but dynamic 1,600-foot diameter dish.
This thing is enormous. Down here, you can see just how ambitious this project really was. It's absolutely enormous. We're driving down into the bowels of the telescope. It's pretty unbelievable that once it was just a little farm in this karst depression, and now it's this incredible structure. From down here, you can really see what's unique about FAST. It uses these actuators to distort the dish. It's got what's called an active reflector. And these are used to tug this huge surface into the exact right shape to collect radio waves. They use 2,000 of these actuators to pull that dish down into that perfect parabolic shape to get the sharpest possible images of the sky.
This system of actuators lets astronomers point each individual panel at any area of the sky they wish, transforming this big, apparently static dish into a dynamic moving reflector.
That is the sound of this actuator starting up, and believe it or not, it actually is moving very, very slowly, about a millimetre every second. These actuators allow engineers to move 300 metres of the dish out of that 500-metre total, and that gives you a lot of flexibility. It allows you to look at different parts of the sky. So rather than just looking straight up, FAST can actually scan a region 40 degrees either side of that so-called zenith. And this really is an incredibly innovative solution they've come up with here at FAST.
But distorting the dish into a paraboloid is just the first step toward unveiling the mysteries of the universe. To make the most powerful radio telescope on Earth, engineers must look to the past.
Oh my God. I just took off an airplane.
To create more impossible engineering. Built deep in the mountaintops of southwest China, engineers have created the most powerful terrestrial tool in space exploration, the FAST telescope.
Scientists wanted to create the world's largest telescope to carry on our global quest to understand what's out there in the universe. And that meant they needed to create a huge dish.
Signals from the universe are extremely weak, and so you need a large collecting area to collect as more signals as possible from the deep space. So that's why you need to build a huge dish.
Even though it can't turn, engineers can alter FAST's enormous parabolic dish surface to collect radio waves from different areas of the sky. But this dynamic element also poses a significant problem. As the reflectors change angles, the central focal point also changes.
This is the sensor cabin, and it's right at the heart of FAST. Once the radio waves have been collected by this giant dish, they're all bounced into here. Now, in order to track a galaxy moving across the sky, you're going to have to keep moving this to keep it in exactly the right spot to look at the object you're interested in.
So, how do you move a 33-ton receiver cabin dangling around 300 feet high and still capture radio waves with pinpoint accuracy? To accomplish the impossible, FAST's engineers must look to the past. They find inspiration in an innovation from 1964, when American engineer Klaus Capell was developing a realistic flight simulator. And science communicator Kate Mulcahy is at L3 Simulation and Training in London, England, to get underneath Capell's invention.
What flight simulation really needed was to recreate the true experience of the sensation of flight. And here they are. Each of these machines weighs over 14 tons and costs a whopping £12 million. These cutting-edge machines are some of the most advanced flight sims available today. You can see here there are 6 hydraulic jacks or actuators. They're positioned in pairs and move independently from each other. And that allows this motion platform such versatile movement.
By employing 6 hydraulic jacks in tandem, Capell created what's called a motion platform, the forerunner to modern flight simulators.
Oh my God. I just took off an airplane. I can't see. What do you do?
Just like a real plane, these jacks allow the motion platform to move the cabin in what's known as 6 degrees of freedom. This includes 3 linear movements: surge, or forward and backwards, heave, or up and down, and sway, or left and right.
Oh my gosh.
And 3 rotations: pitch, roll, and yaw.
This is a crash, surely, surely. It's amazing to think that thanks to these 6 hydraulic jacks sitting underneath this crazy simulator, countless lives have probably been saved. With its dynamic range of movement and its pinpoint accuracy, these motion platforms have opened up a world of possibility across a diverse range of applications.
The engineering team at FAST is raising this innovative motion platform technology to astronomical heights to search the skies with unbelievable precision.
Engineers created this, a lightweight cabin that can be moved anywhere across the surface of the dish, a real innovation. It's 10 meters across, looks like a flying saucer, and it's known as the apple of the eye. In here, we've got receivers sucking all that data and sending it back to the control room. But in order to keep those in exactly the right spot, we've got two different mechanisms at play. First, we've got those 6 towers out there, which tug this cabin into approximately the right position using the servo mechanisms and those 6 huge steel cables.
Not only does it look like a UFO, it flies like one too. Computers control each cable and position the cabin as high as 450 feet and anywhere along a 675-foot trajectory. And like Capel's flight simulator, the cabin pivots by using a motion platform.
For that final bit of precision, we've got those 6 hydraulic pistons controlling this platform, which allows the position to be corrected with incredible precision. Those sensors can be located to within 1 centimetre in this 500-metre dish.
But this breakthrough engineering isn't all that makes the FAST telescope the most sensitive radio telescope on the planet. Truly precise astronomy also depends on the location itself.
Human beings make a lot of electronic noise, such as cell phone, microwave. All the electronic devices make magnetic wave. So all this device is generate interference to our telescope.
To avoid any such radio interference, engineers scope out a quiet, remote corner of southwest China in the Guizhou province, 105 miles from its capital, Guiyang.
FAST is situated in this naturally occurring karst depression, which are a very common feature of the limestone landscape down here in southern China. It's a long way from nearby towns, which might cause radio interference, which would disturb the very sensitive astronomical observations.
But even out here, gathering highly sensitive astronomical observations would have been impossible without one major breakthrough from the past. The FAST telescope in China is the most sensitive radio telescope on Earth, but building it would have been impossible without a key innovation from the past. Astronomer Ryan Lynch is at Green Bank Observatory in West Virginia, exploring how an accidental discovery revealed a hidden universe.
For most of the history of astronomy, everything that we learned about the distant cosmos came from studying optical light, the kind of light that we see with our eyes. But in the 1930s, the dedication of one man changed all of that.
Bell Telephone Laboratories engineer Carl Yansky was trying to eliminate static interference in shortwave radio communications across the Atlantic. To trace this interference, Yansky built a large antenna.
This is an exact replica of the antenna that Jansky built, and it is a work of engineering genius. It's 110 feet wide by 20 feet tall. Now, it doesn't look anything like the current site. I think it looks a little bit more like the wing of an old biplane. But it is an antenna that can detect radio waves from space.
The antenna received radio signals that were amplified by a radio receiver and recorded by pen on a moving paper chart.
The antenna was mounted on a platform sitting on tires that allowed it to rotate, taking a full 360-degree scan of the sky once every 20 minutes. His initial findings revealed a faint but persistent hiss that would rise and fall throughout the course of the day. As he continued to analyze the data that he collected over many months, he realized something truly remarkable. The signal was strongest in the direction of the center of our galaxy. Jansky concluded that what he was actually picking up was radiation from the Milky Way galaxy itself.
Yansky's extraordinary breakthrough revealed a new corridor to the cosmos. Radio telescopes soon yielded groundbreaking discoveries. And in 1964, astronomers used them to actually record the faint echoes emanating from the distant origin of the universe, the Big Bang.
Although it would take the work of later astronomers to really kickstart the field, Jansky's work offered definitive proof the radio waves could be detected coming from the cosmos. His directional movable antenna and wideband receiver form the basis of all modern radio telescopes. Jansky, with his plane wing contraption, is considered to be one of the fathers of modern radio astronomy.
Engineers at FAST are taking this revolutionary radio technology even further and are attempting to detect radio waves emitted by advanced extraterrestrial life. But how do you assemble all the signals from space and transform them into usable data?
You've got to take that phenomenal amount of data and turn it into a picture.
To do this, the team must turn to a game-changing innovation from the past.
They gave programmers the license to dream big.
To make the impossible possible. The FAST telescope in China is the largest and most powerful single-dish radio telescope on the planet. And FAST astronomer Peng Bo is at the center of it all.
It was only a dream, but after 20 years journey, we made it.
FAST can generate a huge amount of data. And physicist Andrew Steele is exploring the groundwork of this enormous accomplishment.
And this is where the action happens. This horn is part of a beam receiver. It slurps up those radio waves and detects how strong they are. There's only one of these here now, but when this thing is finished, there are going to be 19. That puts it head and shoulders above any other radio telescope in the world. But this poses a huge challenge for the engineers and scientists here at FAST. You've got to take that phenomenal amount of data and turn it into a picture.
So how do astronomers and engineers transform radio waves into images? To pull off the impossible, the FAST team must look to the past. Science communicator Kate Mulcahy is investigating an historic silk mill in northern England to uncover the unlikely origins of big data processing.
In the 18th century, garments made from intricately woven fabrics were the height of fashion all across Europe. Looms work by interweaving two sets of thread. The longitudinal threads are called the warp, and the threads running across are called the weft. Now, producing such detailed designs was no easy task, and producers really struggled to meet demands.
To quicken production, French weaver Joseph-Marie Jacquard invented a machine that revolutionized the industry.
And this is it. This is the Jacquard loom. Amazingly, all of these complex mechanisms are actually governed by a few simple cards. This is a card cutter. Skilled workers would use this to translate complex patterns into a language that the loom could understand. The first step would be to copy the pattern onto squared paper, a bit like this. Then for every piece of the pattern that's in a square, a hole would be punched in a corresponding position on my card. Each punch card represents only one line of weave, which is pretty amazing. The next thing we need to do is to take my card, put it into the loom, and that's when the magic really happens.
When the cards enter the head of the machine, the loom's horizontal rods press into them. Each rod controls an individual thread. When there is a hole in the card, the corresponding thread lifts up. In this way, the cards dictate the pattern being woven.
pattern could take thousands of cards. Brilliantly, if you needed to change or amend your pattern, you simply need to load more cards. Whilst the hand loom operator could produce around 2 inches of fabric a day, the amazing jacquard loom could produce 30 times as much. And it only required one person to operate it.
But just how will this breakthrough innovation help fast astronomers transform radio waves into images of the universe? The FAST telescope is the biggest and most precise radio telescope on the planet. At over 1,600 feet in diameter, the dish can transform faint radio waves billions of light years away into stunning images of the universe. But to do this, FAST must process an extraordinary amount of data, which would have been impossible without a breakthrough in 19th century textile manufacturing, the jacquard loom.
One pattern could take thousands of cards. Brilliantly, if you needed to change or amend your pattern, you simply need to load more cards.
This punched card system, with holes and no holes, is essentially an early version of binary code. Jacquard's genius breakthrough changed data processing forever. Inspired by this, American inventor Herman Hollerith developed similar cards for storing information collected from the 1890 U.S. Census. Holes denoted specific meanings like age, gender, and marital status, and were read by Hollerith's tabulation machines, which allowed census data to be collated 10 times faster than previously.
In the 1960s, computer programmers were using punch cards to create, edit, and store computer programs. Incredibly, this is actually a computer program. It's a series of instructions encoded in holes telling the computer exactly what to do. Now, just like the punch cards we looked at earlier, where each card represented a single line of the pattern, here, each card represents one single instruction for the computer. So a computer program could end up being made up of thousands of cards.
By the 1980s, punch cards reached their limits, and programmers began using magnetic disks that could store more data.
Punch cards were the first big step towards building a computer that could be programmed to do just about anything you can imagine. They gave programmers the license to dream big. Suddenly, the possibilities were endless, from connecting the planet to better understanding the universe.
Through the pioneering work of Joseph Jacquard, binary code, and the dramatic advances in computer processing, the FAST team can transform faint radio wave signals into otherworldly images.
Here, this is the supercomputer systems we are building for FAST.
At FAST Central Control, astronomers across the world are using the vast amounts of data to unlock the mysteries of our universe.
The modern radio telescope always try to visualize the radio signals you detect from the telescope. With the computer, you can display these signals with different light curve.
Radio waves travel through space like light, but are invisible to the human eye. To turn these signals into images, astronomers use computer software to label each individual wave with a color code. The buildup of color forms a recognizable visual pattern. But to create such radio images, astronomers must process a lot of data.
We expect the FAST can generate 40 terabytes per night. So we need a huge amount of a storage system. So here we have a roughly 1.6 petabyte storage. And also we have a high-performance computing system to process the data. we can start to try to use telescope to explore a completely new universe that have never been explored before. We are expecting to see lots of the new things.
This is very exciting for astronomers, also I think for the human being, because they'll know some new knowledge about the unknown, about the universe.
Officially completed in September 2016, FAST is now searching the skies further and deeper than ever before.
FAST is going to revolutionize radio astronomy and transform the way that we look at the universe. We just didn't know it was possible to build a dish this big, so we didn't know that you could make a machine this accurate and this powerful.
For astronomer Peng Bo, it's the culmination of a lifelong dream.
I'm very proud to be a member of this team to build a giant radio telescope. So I'm very proud of the achievement you see today here.
By drawing inspiration from the great pioneers of the past, adapting, supersizing, and developing innovations of their own, the designers, engineers, and workers at the FAST telescope have succeeded in making the impossible possible.
FAST is going to allow us to scan more of the sky more quickly than was ever possible before. It's going to give us fresh insight into why the universe looks the way it looks and where it came from. And even more than that, this huge geodesic bowl buried deep in the rugged South Chinese countryside is just an engineering marvel.